In the previous video, we derived the thermodynamic probability for Maxwell Boltzmann statistics. In this video, using this, we will derive the Maxwell Boltzmann distribution law. So let us do that. As in the Stirling's approximation video, you have seen that these things are really big. So what we will do is this, we will take logarithm. So taking log of this thing, so log of omega mb is equal to log of n factorial plus this thing is in multiplication, but when we take logarithm, this changes to summation. So in here we have gi raised to the power ni, but we know that log of m raised to the power n is n log of m. So this ni comes down, ni ln gi. This is in divide, so we know that log of m divided by n is log of m minus log of n. So in here we have a minus sign because of that, and log of ni factorial. In here this also changes to summation, but we take that summation common, and in here this thing is in brackets. Okay, so now after taking logarithm we have this thing. Now in here we will apply the Stirling's approximation to deal with these big factorials. So using Stirling's approximation, we have log of x factorial is x ln of x minus x. So in here we will apply this. So this changes to n log of n minus n plus this is summation as it is. This whole term is also as it is because in here there is no factorial, and minus this changes to ni ln of ni plus ni, because in here this changes to ni ln of ni minus ni, and this minus multiplies with it, so it becomes plus. Now see, summation over I ni is equal to summation over I ni. That means particles in every box, like particles of this box are added to this and so on, which is equal to n, which is the total number of particles. So this thing cancels with this. So we have ni ln of n plus summation of ni ln of gi minus ni ln of ni. So this is what we have. Now we have log of omega mb is equal to this thing. Now to derive the Maxwell Boltzmann distribution function, we need to study our system at equilibrium. And as you have seen in the microstate and macrostate video, equilibrium is the most probable state. That means the number of microstates are maximum. That means we need to find the maxima of this function in here. So how do we find maxima? We first take a derivative and put it equal to 0. If it is negative, it is maxima. If it is positive, it is minima. But in here for now, we don't need to care which type of extremum we get. We will just take the derivative and put it equal to 0. Okay, so let us do that. We will take the derivative of this thing in here. So taking derivative of this, in here this thing is constant, so its derivative is 0. So this thing vanishes and we have this thing derivative of this thing in here. Now we will take the derivative of this inside thing. In here be very careful. So let us take the derivative of this thing in here. This gi thing is also not subject to variation. This ni thing is what is subjected to variation. So constant times the differentiation ln of gi dni. Now in here we have a minus. Okay, we have first function, derivative of second function. Derivative of log is 1 upon x, so in here 1 upon ni, and then we will apply chain rule, so dni in here. Now in here we have a minus sign, we will like multiply it in here. Then we have second function and derivative of first function, so we have this thing in here. Now this thing cancels with this in here. Now we are left with this. So in here you first need to know where this 1 goes. So as you know that this ni, summation of ni over I, is constant. Okay, because ni is the number of particles in each box, and summation over I ni is equal to n, the total number of particles, which is constant. If we take its derivative dni, now ni locally is not constant, the particles are changing, but the whole summation of this dni is 0. So in here this is, we have this ni cancel this, so we have summation over I dni which is 0. So this thing in here is 0, so that's why this thing vanishes. Now we have this. Now we will take this dni common. Now inside we are left with log of gi minus log of ni. Now we will take a minus sign common and we have log of ni minus log of gi, and we will apply log of m minus log of n is equal to log of m divided by n. So in here we have this dni common, log of ni divided by gi with a minus sign outside. So this is what we get after applying this derivative. Now under normal functions like x square or some other functions, when we apply the derivative and put it equal to 0, we find the maxima or minima easily. But in here, the function that we are taking is also subject to other constraints. So we need to take account for those constraints to find the maxima or minima. And the constraints are the total number of particles. This thing is constant, that means this is 0, and the total energy is also constant, that means this is 0. So these are our two constraints. Now what we will do, we will apply the method of Lagrange's multiplier in here. That method in itself is a very different and a deep topic. So in simplicity, what we will do is this: we will multiply this term with something like alpha, and we will multiply this term with some other thing like beta, and we will add this in here. Because this is equal to 0, it won't change anything, but it will help us take account of those constraints also. So now applying the method of Lagrange's multiplier, so alpha plus beta ei, and this dni is common outside. So we have this function. Now this is equal to 0. After applying these constraints, now we can say this is equal to 0 at maxima. That means the number of microstates are maximum. Okay, so we have this thing in here. Now if this is 0, this inside thing is also 0. So we will write it like this. Now we will take this to the other side like this. We are just approaching our function. This ni upon gi is e raised to our minus alpha plus beta ei, and now we will take this gi in here, and this will go to bottom with a plus sign in here, and this in here is the Maxwell Boltzmann distribution law. The only thing unknown in here is these Lagrange's multiplier. Now what we will do is this: we will derive the Bose-Einstein, Fermi-Dirac, all three distribution functions in this form, and then we will determine these Lagrange's multiplier. Because for all three functions, these two are the same. So we will derive these at the end. For now, this is a general form of the Maxwell Boltzmann distribution law. But we can see what these values comes out to be. So we know that this ni upon gi determines occupancy. We have talked about in the statistical mechanics in a nutshell video. You must watch that video if you want to understand why statistical mechanics is the way it is. This tells us how many particles are in which energy level at equilibrium. So we will denote it by F. And after deriving this alpha and beta comes out to be, this beta comes out to be 1 upon kBt, and this alpha comes out to be minus mu upon kBt. So after putting all this, we have this thing F is equal to e raised to the power minus ei upon kBt minus mu upon kBt. So this is the more familiar version of the Maxwell-Boltzmann distribution law, which is after putting these Lagrange's multiplier. This thing in here F is ni upon gi. So you can like keep it in this form also. So this was the derivation of the Maxwell-Boltzmann distribution law. Now, as I promised in every video, I will share a reward to you at the end, something interesting. So in this video, I will share a riddle, which is this: where can you find rivers with no water, cities with no buildings, and forests with no trees? And the answer is on a map. So this was a fun riddle. You can ask it with your friends. So thanks for watching this video, and always remember that math is everything.